Okay, thank you very much. So it's a great pleasure to be here. We had this introduction about these European styles. I remember I took a course as an undergraduate in kind of giving presentations, and we were like a relatively small group, like 20 students or so. And we had this like talk in a very small lecture room for 20 people. And after I gave my presentation, a teacher said to me, "You scared me. You were kind of intimidating and loud and so on." She said, you need a bigger stage. So I think this is appropriate, and I can talk to you here, so hopefully I don't scare you too much, even though this subject could be one of those which actually can, for some at least, be, if not intimidating, potentially scary. Will we be taken over by these artificial intelligence entities? I think that's a very interesting question. So what I want to do here today is to try to, in some sense, address this hype and this, there's a lot of talk about AI, but what is it really, at least from our perspective as researchers? And how does it relate to your professions? I am not an expert in your field, so actually I will not say that much about it. But I will try to connect to it where I see it. And I'm sure you will find ample of connections by yourself. And also touch upon this European approach to AI and these ethical guidelines that we have developed here in Europe. So I was part of that group as well. So basically, I should say some words about my background. So I've been doing AI research for more than 20 years. And actually what we were doing was building autonomous helicopters, so unmanned aircraft systems. So more than 20 years ago, we had fully autonomous helicopters. And what we were doing, we're basically integrating a lot of different AI technologies into working fielded systems. And we actually collaborate also with first responders and so on to help with accidents. For example, if there's been some major accident, to quickly get an overview, to identify injured people. And if it's, back then it was the tsunami in Southeast Asia. That was a big thing, to how can we address and help out in situations like that. And today I both have my own research group. I also work more on the policy level. So why is there so much interest in AI? I would argue that one of the reasons is that we see these kind of applications that are kind of impressive, like self-driving cars, which was like the thing 5 years ago or so. Today, people talk a little bit less about it because it turned out that was actually much, much harder than what they initially thought, which of course does not surprise me particularly. But I do think it's very telling that you relatively, well, it just took 15 years or so, but relatively quickly can get some kind of commercial prototype. But to actually get it to robustly work in basically every type of situation, that is a much more challenging task, which of course they're still working on. But I do still think it's a very interesting and important application. And then, of course, we have all these games like chess, Go, poker, StarCraft, Dota, and so on and so forth, which the computer is better than humans at. I think it was Bridge. That was like some months ago that a computer were beating the best players in Bridge. So basically, every type of these games, it's very clear that the computer is significantly better than we are. And we are starting to see other applications like this Copilot from GitHub, which is kind of writing code automatically. So basically filling in code for you by learning from all this open source software that's stored on GitHub, which is kind of interesting. And then there was kind of making some noise a month ago was this DALL-E, where you basically type in a sentence and the computer can generate photorealistic images showing what you typed in. So the picture with the teddy bears there, or well, it's everywhere now, but was basically it's like teddy bears dressed up as cyberpunks or something like that. And then the computer came up with this. So I think that's quite impressive. So, and behind all of these different applications, we see this concept of artificial intelligence. So, as a first order approximation, you should say, I mean, the point of AI is really how can we make the computer do things that we assume require human intelligence. So if a human were to have to be intelligent to be doing it, then and the computer can do it, then well, then it can be intelligent. So basically, get the computer to do things that currently only people can do. Which of course has the interesting consequence that as soon as the computer can do it, well, it does no longer count. So therefore, the frontier is always moving, and I think that's one of the fascinating part of this field. So another example is this, which I think is both interesting and relevant, especially to this audience. So this looks like pictures of people just like you and me. But the interesting thing is that these are then computer-generated images. So it's actually come from the URL thispersondoesnotexist.com. And so basically, the computer has taken a large number of photos of real people and then learned what does a face look like, kind of. And then it can then produce new images that look like faces. And of course, this has a number of interesting consequences. First of all, it makes this question of when you see something, whether it's online or in a paper or something, how do you know that it's real? And what does real mean anyway? But because, I mean, it was this incident, or incident, not an incident, but it was this case in I believe it was Japan, where it turned out that one of the TV personalities was actually generated. So it didn't even exist. But of course, people created a relation to this thing. Well, yeah. But so in some sense, it does exist. I mean, it's clearly something that people relate to. So it exists, but yeah, you know, it's hard to tell what's true and false these days. But of course, this also raises questions when it comes to authenticity of evidence and so on, which I guess is bread and butter for you. So how do you determine this? And actually, in the session that's later that was already mentioned about this AI session after lunch, there will be a paper about how to detect whether something is a deep fake. So if you want to learn how to detect this, you know where to go after lunch. So of course, this asks a number of questions. But it can also be used for good things. I mean, for example, there's a lot of data that we currently cannot use due to privacy and legal issues and so on. But then we can actually take this sensitive data, we can lock it up in some room in the basement with no connections. We can train models such as this, and then we can generate computer-generated data with the same properties, or similar properties at least, that the real data has. And then we can use this synthetic data instead of the real data. And actually, I have an ongoing master thesis with the police in Linköping, or the forensics in Linköping, on this, how to train, to actually use this to train faces, so they can use that for training up facial recognition systems. We are also doing other things. It's also been used in medicine. So I think this is a technique that's here, and that's very relevant to be aware of. And that both proves or kind of causes challenges, but also opportunities. So that's just one particular example. So what is then AI? So of course, this is kind of the million-dollar question these days. Actually, I don't really believe that there is one definition that's kind of meaningful. I think, of course, we can have a very generic definition that kind of captures a lot of things. That's fine. But to actually have a specific and kind of pointy definition of AI, I don't believe that's possible. And the simple reason is that it's such a wide and multifaceted topic. But here, at least, I have three definitions that I think kind of shows different aspects of what it is. So the first comes from John McCarthy, who was one of the founders of the field. So actually, they sent in a research proposal in 1955, where they wanted to do a summer project on this thing that they called artificial intelligence, and that they were planning to solve this in 2 or 3 months over the summer. Of course, now 70 years later, we're still working on it, and I believe 70 years from now, we will still be working on it. But so it's a very good proposal, I guess. So what he proposed then was that AI is the science and the engineering of making intelligent machines, especially intelligent computer programs. And I think this is one of these kind of general, broad definitions. But the challenge here is, and usually what's the kind of argument against it, is what is intelligence? And actually it turns out that there is no commonly agreed upon definition of what intelligence is. I looked it up a number of years back and found a survey, I think it was from 2007, which had 71 different definitions of intelligence. So I guess we can multiply 3 by 71. Yeah, we can get many combinations. Anyway, so there is no, so we don't agree what that is. I mean, you could take one example. We can take an IQ test, for example. You know, you get the number of boxes, and you have to find a pattern, and then select the right box in the final column. I mean, this is something that's completely trivial for a computer. So if you measure intelligence by IQ, of course, the computer has the highest possible score you can get on these tests. Because, I mean, finding these patterns is exactly what a computer is great at. So that's trivial. So maybe that's not the best definition of intelligence. So a different definition comes from the EU. This is the EU session, after all. So there, the definition is that AI refers to systems that display intelligent behavior by analyzing their environment and taking actions with some degree of autonomy to achieve specific goals. And I think this is a good definition in the sense that it actually describes what do these systems do or how do they work. Well, first of all, they're designed by people, so someone decide what is the goal of this system, what do we want it to do. And then it needs to collect data or information from its environment, and then based on this information it's collecting, make decisions on what to do in order to achieve the goal. And then this taking action with some degree of autonomy means that you can have everything from a decision support system, which basically just makes a recommendation, and then it's up to the user to determine what they want to do with this information, to, say, for example, an autonomous car, which is then making all the decisions itself, and it needs to deal with all kinds of varieties and everything in between. And of course, here we don't really care how they work on the inside, but we only care about what do they do. So if they have this, if they can do things that we believe require intelligence, then we agree that it's an AI system. And then the third definition that I also like is from AAAI, which is the Association for Advancement of AI, previously known as the American Association of AI, where they say that it's the scientific understanding of the mechanisms underlying thought and intelligent behavior and their embodiment in machines. So here we have not only this intelligent behavior, basically the external perspective, but also how do the cognitive mechanisms work, and how can we understand them well enough so we can actually mechanize them and implement them in computers. So it takes both this external and the internal perspective. And so I think that that's a very nice view as well. And personally, to me, it's really about this. How can we understand this abstract concept of intelligence well enough so that we can actually build engineering solutions, systems based on this general concept? And the analogy I usually use is from if you want to build a flying robot, you can study birds and try to build a robot with flapping wings. It is possible, but it's very expensive and hard and so on. Or you can study birds and learn about aerodynamics, and then use engineering to build airplanes that can go faster, higher, take more cargo, and so on and so forth. And I would make the same analogy. We want to understand the abstract concept and then build engineering solutions based on that. So that's some further views. I think one also interesting and important distinction here is between digitalization in general and AI more specifically. So usually, I mean, my argument here is that digitalization is all about how do we make the world square enough to fit into the computer. And basically, we, the humans, have to define every concept that we use. We need to define every step in every process in minute details. And if we can do all that, well, then we can implement it in a computer and we get a lot of benefits. We can scale it up, we can handle much larger volumes of data, we can do it much faster, we can repeat it over and over again without any mistakes. So of course there's this huge advantage of digitalization, but it's we, the humans, who do all the work, and then the computer just repeating what we told it to do. So of course this is very useful. However, there are things that are very difficult to define, problems that we cannot define. And the classic example here is computer vision. How do you describe to a computer what a simple thing such as a chair is? So that it only recognizes chairs and does not also include tables and stools and I don't know what else. So there are so many other things that are so similar. So it's virtually impossible to come up with a definition of a chair that only covers chairs. And here I think AI is very useful. And it's also when you have unanticipated situations. So if you are actually building an autonomous car, you need to deal with anything that happens. Because not doing anything is, well, either not an option or at least also an action. So the computer cannot say, I don't know what to do in this situation, so, well, I don't do anything. Especially if you're traveling in 70 miles per hour or something like that, then that will have consequences. So you need to deal with anything, especially those things that the engineers never thought about, because those are the interesting things. And then also unstructured data. So I think here is where we see the real advantage and the major use today is really about unstructured data. Because we have all this text and images and videos and so on and so forth, which doesn't fit into this nice structured database format that is required. But and now you probably have tons of data that you don't use. And here AI is extremely useful because it can find the patterns. It can use to understand what is the important parts here. Well, I shouldn't use understanding, but yeah, identify things that seems to be relevant for the task. So there is the use. And actually, I think it's a very natural progression that we start with this digitization. We basically take what we did analog and we do it digitally. For example, we previously probably had paper. You used internal mail service and sent the papers around within your organization. Then you replaced the papers with PDF and you used email instead of the internal mail. But you do exactly the same thing as you did before. You haven't really changed anything, just digitized your activities. And what happens next? Oh, of course, then all the organizations collect massive amounts of data. So now we have data warehouses, data lakes, and I don't know, all these huge amounts of data, and most of it is never used. And again, I think that's why it's so natural that today AI is making a big impact and has this, provides this value to organizations. Because it can structure, it can analyze and structure and turn this data into actionable advice. So that I think is important. So what is then AI? I mean, I talked about these definitions, but I mean, if you look at the more technical point of view, I mean, AI is a huge field. There are so many different subfields within AI. But the fields that today are kind of causing the most interest is machine learning. We can have a whole debate about that at a different time. And especially one particular type of machine learning techniques, namely deep learning techniques, which is actually a rebranding of a technique that was invented in the 50s. But never mind. So what is then machine learning? Well, machine learning is in some sense really, really simple in the sense that it tries to take data, apply some form of learning algorithm, and then generate or produce a model that allows you to answer questions or draw conclusions or get insights from this data. And more, And so just to give a trivial example, so in some sense, the simplest possible machine learning model is linear regression, which I'm sure a lot of people here already know and use on a daily basis. It was invented in the 19th century, by the way. But it still gives us a lot of useful, because we take this data, so of course, very American usually use this kind of data. So here it's about apartments being sold. So we know the size of the apartment or the size of the apartment and how much was sold for. We have a bunch of observations. We can then try to find a straight line which minimizes the average error, and we get the line, the red line there. And what's interesting is that this red line is then our model. It allows us to answer questions based on where we don't have any data at all at the moment. For example, it's kind of hard to see, but there are no data at 3,500 square feet, but still we can get an estimation. What would we get for an apartment of that size? So it allows us to answer questions even if there's no particular data. So it's about generalization. So it's about generalization beyond the data. And what are consequences for that? Well, first of all, there's basically no, or maybe two or 3 points there that's actually on the line. So it's not about capturing the data exactly. It's about finding these underlying patterns. So I think that's a very important part, because people use, oh, well, it didn't match the data. I said, no, that's not the point. Because, of course, we could just have a polynomial of sufficient degree, and we can exactly match the data. We will get a very squiggly line, and it's kind of useless as a model, because it's completely overfitted to the data. So that's a very important part, that we want to find the underlying models, or the underlying patterns, I should say. And I think it's also important to realize that in real life, the data is messy. So here we just have a trivial example generated that basically want to separate the green circles from the blue triangles. And we see that there is no way to draw a straight line to actually separate these, which means that it's impossible to come up with a model that correctly 100% classifies these two things. But then we can also increase the flexibility. So the more flexible our model is, the more we can shape the model to the data. So for example, in this particular case, if we go from a linear to a quadratic model, now we can have circles and so on. Then we can see that we can capture data slightly better, or at least better. So in some sense, what we want to do is then to increase this flexibility so that we can actually capture the pattern of the data. And of course, this is where these neural networks come in, because they are in some sense infinitely flexible. You can just add layers and nodes and so on, and then you can get very, very high flexibility and be able to capture also very messy data. There are many other techniques, for example, transforming the data or adding other dimensions to the data, so you have multiple dimensions, and then hopefully in this joint space you can actually separate your classes. So what are then the main types of problems we want to do? We want to do classification. So the classical example here is object detection, so that you might have, for example, a store, and the store has 1,000 different things that it sells, and now you want to have an automated cash register, so the thing goes by your camera, and you want to classify which of the 1,000 things that you have in your store is this. So it's about the classification. But we also have this regression, which was the example with the house prices, where we wanted to have a function that can answer any question. And we have the generative models, where you basically learn a probability distribution that you can then sample from, like with the example of the faces. So basically you get a probability distribution of images, which are the ones that are likely to be faces, and then you can sample from this. There are also a large variety of different methods for actually doing this machine learning. And the most common one is what's called supervised learning, where you train the computer by giving examples. Like, if this is we had the example with its house prices. If this is the size of the house, this is what you got. And then you have a large number of such pairs. You can have also, for example, this learning to classify the objects in your store as another example. So basically, you program the system through examples. So for every example you show it, you need to tell it what the right answer is. And then it learns this mapping from input to output. So it basically learns a function. So neural networks are, for example, function approximations. You can also have unsupervised learning, where instead, so you don't know what the right answer is, but rather you can find patterns in the data, for example, clusters and so on. So are there data points that are similar to each other, and then we can call them things. Reinforcement learning is a third category, where you basically learn through trial and error, which is very common in, for example, robotics. So you want to train a robot to do something, then it will try the action, and after each action it will get some reward, either positive or negative. Positive if it was a good outcome, negative if it was a bad outcome, and then through this process of trial and error, it can learn what to do in order to achieve some objective. This is also what's being used behind these games like AlphaGo and so on, where basically the computer is playing against itself in a structured way in order to learn how to play the game optimally. So there's a large variety of different techniques. So now let's go back to these neural networks because they're popular. And neural networks is an extremely simple mathematical model. It's basically a weighted sum of inputs that's transformed through a nonlinear activation function. So each of the... Do I have a pointer here? No. Anyway, every node in the network is basically just taking each of this. So basically each arrow here is a weight. And you multiply the output of the node with the weight, and that's the input to the next level. And then you sum this up, and then you throw that through an activation function, which is basically linear regression. So what we basically do is a bunch of different linear regressions, and then we combine them in this hierarchical manner. And the training process changing the weights of this, so that you get closer to the desired output. So for example, assume that the top left node should have 4 as the output, and it just turns out 2 this time, so it's not enough. And if the weight is positive, and if the input node is positive, then we know we need to increase the weight slightly. Or if it's a negative weight, we should decrease it slightly, and so that we get closer to 4. And then basically you train this iteratively in order to find the optimal set of parameters to capture your data. So it's a really simple model. And it actually has a very fascinating history because actually this model was invented in the mid-40s by my colleagues in Pitts, where they were studying human neurons and made this very, very simple mathematical model of how human neuron worked. Then in the 50s, the first artificial neural networks were built. Claude Shannon and others were involved, Frank Rosenblatt. But the problem was that they could only train one-layer networks. They didn't know how to train multiple layers of networks, so they could only do 2-layer networks. And then in the late 60s was a very famous book, Perceptrons, where they proved that if you only have 2 layers of network, you cannot represent either or XOR function. You cannot have nonlinear functions. So it was kind of not that useful. And all the research died out in the 70s around this. And then in the mid-80s, people discovered, so Jeffrey Hinton and others discovered this gradient descent or backpropagation method to train multiple layers of networks. So now we're in the mid-80s. What's fascinating was that the same technique was actually discovered by a Finnish master's thesis 10 years earlier. It was also discovered by a Japanese researcher a few years earlier, but of course, Americans always get the credit. But anyway, they were the ones that really popularized this. And then in the early 90s, there were some other advances, for example, done by John LeCun and others on these convolutional neural networks, which I will not go into too much detail on. And then in 1994, it was proved that a neural network of sufficient size, trained sufficiently long with sufficient amount of data, can approximate any function. So it's proved that it is a universal approximator, which means that it can actually, in theory at least, capture any well-defined function. So that was in 1994. As a side note, I did my kind of final thesis in high school in 1995, and then I implemented neural networks, and that was not a strange thing. I just go to the store and buy a textbook about how do neural networks work, and I could implement it. So, and that was the mid-90s. And it's been used since. But what really made the difference was, of course, when you start to scale things up after, the internet kind of revolution and so on, because suddenly you had millions and millions of images and data and so on, and you had a computing infrastructure. You start to use the GPUs of the kids' graphics, gaming computers, and start to use it for this, and then you could scale this up and really make a difference. And now we're talking 2010, 2012, I think was in some sense one of the breakthroughs. So that's 10 years ago today, and today it's basically used everywhere. So I think that's an interesting story about that. And of course today it's been added, but basically it's about having different types of layers, and you combine them in different ways. But the general techniques has been around for some time. And what's really interesting is, of course, what's the impact of these technologies? So for example, one of the areas which have been basically revolutionized through these techniques is image recognition and image classification and computer vision in general, where there's been this competition around this ImageNet dataset. So basically, a large data set with standardized images, and everyone can submit their program to be able to classify these 1,000 different objects. And what you can see that around 2010, the error rate was around slightly below 30%. And then in 2012, so in just one step by applying these deep neural networks, AlexNet, it went from slightly more than 25% to 15%. So in one step, it was 10% less. Or well, not 10%, well, you get the point. So it's a huge step. And then the techniques were developing, and today these techniques are superior to human object recognition by far. And we see exactly the same development in speech recognition. So there was a lot of research on speech recognition in the 80s and 90s. And in some specific domains, you can make progress. So for example, booking travel. So I think the Swedish railways have been using this recognition, and apparently they have problems with people from the south of Sweden, where I'm from. But anyway, in most people they could understand, and you can do simple things in well-defined domains using these speech recognition techniques. And then, but in this more general conversational speech, the progress were, of course, there was some progress, but that it flattened out. And if you're a researcher, you know if you don't make progress, funding dries out very quickly, and basically everything died out. But then again, in the early 2010s, people start to use these deep learning techniques, and we see exactly the same progress there. That it started out with this word error rate of about 16%, so way too many errors per, too many words per error, so it's basically useless. But then you, through successive improvements, 5-6 years later, it was on human level. And again, today, these systems basically work in order to understand speech, or rather to translate spoken language to text. And today, we can use this in a multitude of different applications. So I think that's another one of these really interesting examples. But I think there is one challenge, and that is how do we evaluate these systems? I will talk more about that later. But the thing here is, as I showed, it's very difficult to actually capture the real underlying data. I mean, many of you are probably data scientists and working with this, so I mean, you're well aware of this, but that we have this kind of true positives. Those are the ones we really want to capture. And then we have the false negatives, the ones that are true cases that we don't find, and the false positives that we also want to avoid. And of course, what we can do here is that in some sense, we can increase the size of the circle here, so in some sense making our model more flexible, and then we can cover more cases. So then we cover more of the positives, but we also get a higher false positive rate. So there is a trade-off here between this precision and recall. So usually we cannot get both very high precision and very high recall. And here we have a challenge. And of course, what you want is domain dependent. So, for example, if it's going to be used in a medical application, for example, to detect cancer as one common example, then you really want to avoid these false negatives. So in some sense, it's better to have some false positives because you will then do more studies, and then you find out whether it's a real case. But you could take, for example, a police case. If you're actually, for example, going to arrest someone based on this, then probably you don't want to have high false positive rates. That might be the worst thing in that case. So then you have to kind of train your system differently. So this is really important to keep in mind. So what are then the applications of AI today? Well, I would say that the areas where we've seen the most impact is really everything what we call perception. So basically understanding the world around us, for example, through computer vision. So actually, in some sense, I could have taken the nice video that was shown in the introduction here today, and basically every one of these examples you can connect to different areas of AI. So I mean, for example, this identifying people in images or matching things over time. And so on. So computer vision is one major area. And I believe there's actually another paper in the AI session on the use of computer vision. our image recognition techniques. Voice recognition, so here you can you determine whether some voice sample is coming from this person or not? So identifying the identity behind voices, for example. Natural language processing, how to take this huge amount of textual data, structure it, find the connections, and summarizing and translating, and so on and so forth. So a huge number of different applications. Sentiment analysis is another one, trying to predict or trying to guess if there's some unrest coming through what's being talked about in social media and so on. So again, natural language processing, another one of these areas where it's huge progress and a huge number of applications. And of course, in general, how to deal with large-scale data analysis. So this was some introduction. So now I have 2 questions for you. So now you have to take out your apps. And the first question is, when do you think AI will change the way you work in your organization? And you get, let's see, 7 alternatives, depending on the time scale that you think it will take. Ah, interesting. So what we can see is actually the majority, the largest of these 7 alternatives is actually, it's already being used. So I think that's a nice thing. But we also see that in some sense, the second largest is like, what was that, 6 to 10 years? No, maybe 3 to 5 years. I don't know. So it's kind of interesting. Either you do it now, or you think it will actually take quite some time before you get it. Ah, that's interesting. 148 votes, not bad. If we take the next slide, please. Yeah, 3 to 5 years. At least it was not that many said never. That's good. Now we have the interesting question: when would you like it to be? So in some sense, now you said that what you think it would be for your organization, but what would you like it to be from your personal perspective? And the same alternatives. I guess we can now verify that there was 50 that said they were already doing it. So yeah, that's 53. That's good. So here we see a different pattern. So basically, you wish it were happening sooner. And I think this is very typical behavior in some sense, that organizations are a bit, what you say, slower than what many of the employees wish they were. So I'm not particularly surprised. And then, there's one that hope it will be never as well. That's good. We always want someone each. Yes, always someone that, yeah. We need people of all kinds. Very good. Thank you. So now some challenges with AI. So I talked a little bit about what it is and what some of the applications. So what are some of the challenges? I think one major challenge is that in some sense the AI part or the machine learning part of a system is really kind of tiny. It's not the big thing. Of course, you need qualified people for that, but usually you need a lot of infrastructure and support around it to deal with these large amounts of data. You need to deal with large amount of computing infrastructure and so on. And I really think this is a challenge for many organizations. So I work with a few, and even if they're competent, technically competent organization, usually they are not set up to deal with this kind of data-driven applications. And I also think it's not strange that it's companies like Google and Amazon and so on, which in some sense are not really AI companies to start with, but they have all the infrastructure. So adding the AI part when you have all the infrastructure is really not a major deal. Of course, it's not trivial, but you have a lot for free. And I think this is also a challenge for, if you talk in this European perspective, that many European companies lack this infrastructure. And of course, we haven't started to talk about the public sector. So of course, we also lack this kind of infrastructure, which makes it difficult to actually take advantage of this large-scale data analysis and data processing tools. So that's something to keep in mind. So actually, when we work with companies and organizations, usually it takes a year or two before we get the infrastructure and the data pipelines and all these things set up, so that we can actually start to do some AI and machine learning parts. So that's something to keep in mind. We also know that machine learning is brittle, so that small changes to the input, especially if you take, for example, this image recognition, small changes to the input can make a major difference on the output. So in this case, we have an example of a panda, which relatively low confidence. We add something that looks like noise. We get a new image that actually still looks like a panda, but to the computer now looks like a monkey. And it's extremely confident about it as well. So I think here we have one of the challenges, that it's really difficult to kind of guarantee the performance of these systems. Of course, this particular example is constructed. So for those that know your math, this is basically taking a step in the gradient's direction. So this is what you then use to train the system. So you can generate data that can then use to train the system. But it's still a challenge. Another challenge when you have these data-driven techniques is, of course, that you get bias in your data. And there's a huge number of different types of biases. In some sense, the simplest and most common one is, for example, data set bias. So basically, your data set is not representative of the particular application that you want to do. And the classical example here is a facial recognition system, which worked pretty well on white men, but did not work on colored women, for example. And then when you look into it, it turned out that they basically had trained the system on themselves, which of course the developers was mainly white men. Some Asians as well, so it worked reasonably well on Asians too. But then, of course, there was clearly a problem that the data set was not representative. However, this is a relatively simple thing to fix, in the sense that it's about collecting more data. And as you collect more and more data over time, your data set will be more representative as it becomes more varied and diverse. However, there are other types of data sets. Of course, actually, we have one problem in what is representative. I mean, for example, if we do a facial recognition system in Sweden compared to doing it in India or doing it in China or something, I mean, of course, what's representative is very different depending on where you are. So that is, of course, a challenge. But actually, a different type of bias problem is when your data is not, or rather the world is not as you wish it were. And one of the examples here is about providing job ads. And it turned out there was one of these job ad services which was more likely to show an ad for a higher paying job to men, and it was more likely to show an ad for a lower paying job to women. And if you look, why did it do this? Well, basically it was looking at what is the kind of employment statistics. And women were more like, or rather it's, and then combine that with pay discrimination based on gender. That jobs which mainly women take are lower paying than jobs that men usually take. So how do you do it then? Because you cannot collect more data. I mean, more data would just verify that this was the case. So actually you need to actively change the way you deal with the data. For example, you can, well, show all ads to everyone. So in some sense, which of course is a consequence that, I mean, you might show ads to people that they're not interested in, because it should be, well, you ought to be interested in this more than you actually are interested in this. Or you actually have to manipulate the data in order to get the desired kind of statistics of the data. Which means that someone needs to make a decision about how do we want the data to look like, and then you have to generate the data according to that pattern. And now, of course, because who wants to take responsibility for that decision? Because we know that whatever that decision is, it will always be wrong, because there's always someone who will think it was wrong at least. And I mean, it's completely obvious that companies like Google and Facebook and so on don't want to make this decision. Because, of course, they know that whatever they do, they will be blamed for it. So they try to say, we're just using your data. You are controlling this by the way that you behave. Which I don't think too many people buy, but anyway, that's the argumentation. And I really think that is a much more challenging question. When the world is not as we wish it to be. And how do we deal with that? So that's another interesting thing. And we also have this challenge of AI and organization. that in order to succeed, we really need to combine domain knowledge with technical knowledge. We need people that understand the technology sufficiently, but really understand the domain, the problem that you're actually working on, to understand how should we use, what techniques should we use, where should we use them, and so on. And talk to these engineers that are difficult to talk to. And really need this kind of combined competence. And I really think that is another challenging area. How do we get these combined competences? But we also see that the organizations that we have today, which are usually hierarchical, that do not work. And the simple reason is that the data that's being generated in one part of the hierarchy, it's needed by a completely different part of the hierarchy. And, well, you probably know that talking between the silos or the different branches is not an easy thing, especially if the cost is in one part and the benefit is in a different part. So we really see this, that it's a really challenging to introduce this in this centralized, hierarchical organizations. We really need to break down the silos to reap the benefits. And another thing which is difficult for many is this, that you will not be able to do everything yourself, which means that you need to collaborate with others. So you really need to work in ecosystems, which means that you have to open up your data and your processes and so on to others, so that they can build upon this and feed it back to you. And really having this interaction in a more open ecosystem. And again, that's a challenge for many, but needed. And then we come back to this question, how to evaluate AI systems. So this is an example of this Google DeepMind AlphaGo and beating KG a number of years back, and he looks a little bit sad there. And after the game, he said that he felt that he didn't have a chance against the computer because the computer was playing like a god. And I think that's an interesting statement on its own, but we will not care about that. Rather, we want to see how did the human expert commentators commentate these games. And it was several times during these, especially this Move 37, which is kind of famous, the expert commentators said something along the lines of, haha, the computer made a mistake. A human would never play like that. And of course, we know the computer won, which means that objectively, this was a good move. But from the human expert perspective, it looks like a bad move. Now, of course, this is kind of completely, it doesn't make a much difference if you lose or win in Go, unless you're KE or some of these other guys. But now take this was a medical decision instead. And you are a medical doctor. You have this tool to help you diagnose, and the system proposes a diagnosis that's completely strange to you. You cannot see why this diagnosis should actually be correct in this case. How should you know that you know better than the computer? On what grounds should you change this decision? It could actually turn out that was actually correct and would potentially have saved the person's life if you did it. Of course, it could also be the complete opposite. That, the advice was really bad and you should not take it. So on what grounds should we follow or violate or not? Well, should we decide on what to do with this information? That, I think, is a really major challenge. So now let's go back to these games. So, chess is one of these games where we humans haven't had a chance against the computer for, well, more than 25 years now. Garry Kasparov lost in 1997 against IBM Deep Blue. So apparently computers are definitely better than people. But what's interesting is if you combine AIs and chess-playing machines and humans, they're better than both the best chess-playing computers and the best people. So actually, I think this is another interesting story that, Garry Kasparov lost. He was really upset and angry about that. But then he realized, I have something to gain here. So he started to make these chess-playing programs. So, of course, now he makes a lot of money from building these chess-playing machines. What's also interesting is that he came up with this idea of having these human chess-playing machines competitions. So he was the one that organized this, and where it turned out that the combination was better. And his analysis of this was that the computer is much better at the tactical part. So when you know what to achieve, finding the optimal way of achieving that, that's what the computer is great at. However, this more strategic thinking, like what are the objectives we should achieve, that humans were still better at. And what's also interesting was that it's a different skill to play chess with a computer compared to playing chess without one. So you really need to work with competence development and update or changing your organization. So it's not really or at least not a purely technical problem, but it's much more an organizational problem and a kind of business development problem. How to integrate these techniques into existing activities. And actually, there is an example. There was a report done by the Swedish digitalization agency, I think a year and a half ago, where they studied, how much money could the Swedish state save every year by applying existing AI technology to existing processes. And it came up that they estimated to 140 billion Swedish kroners per year could basically be freed to better use through AI technology. So that's 14 billion euros per year that could be freed for other things. And what do you think happened? Well, nothing. But another interesting story along those lines is that now what happens, now we start to analyze, we start to build these models of human decision making. It turns out we don't really like that. So here is an example. So in France, they made the data available for all the decisions made in court. And of course, what happens is that some researchers start to study the way that the judges make decisions, and basically came to the conclusion that in I think it was immigration cases that they were looking at, it was only depending on which judge you got, not on the actual circumstances of the case. So basically, it turned out that, the judges were not maybe as, fair that you would have liked them to be. But to me, that's not particularly surprising because we know that all human decision makings are kind of, have different issues. But what's very interesting, what happened after they published the report, well, first of all, they didn't want to comment the report first. But after the report was published, they became not so happy and actually made it illegal to study how individual judges make decisions. So instead of learning how can we improve and make our legal system better, they made it illegal to do it. And I would not be surprised if we see more of these kind of cases. But I really think, from my point of view, it's like, well, we should have known that from the start. It's like, now we really have the opportunity to study our own decision making from the outside. We can actually have a kind of outside perspective on our own decision making so that we can learn what are the mistakes we're doing and how can we improve. But then I'm not a French judge. Anyway, so why is AI different? Well, I think there's a large number of differences. So, for example, we have scale, speed, and this single-mindedness that, usually you don't replace one person with one system, but rather maybe 10 people with one system, which means that you become more sensitive to errors. Because previously, all these 10 people probably made some mistakes every now and then, but there was always someone else to catch that. Now you have a single system making all the decisions, and of course, if that is making mistakes, all the decisions might be affected. And you also have scale that now you might have, instead of having a handful, you might have thousands or millions of cases. And of course, even if you have an extremely small error rate, if you have 1 million cases and just 1%, it's still a lot, 10,000 errors, just because the scale of things. And of course, we also have the speed, that things go much faster, and it becomes challenging for us to keep up. But I also think it's interesting that in some sense, these systems cannot break the rules. So they're programmed in some way, and they would do exactly what they're programmed to and nothing else. Of course, sometimes we don't understand what we're programmed them to do, but we still did. So they cannot break the rules. And I'm quite sure that none of our organizations would work if we actually followed all the rules. So it's more a question of which rules should we follow, because usually the rules are contradictory as well. So if we had to follow all the rules, we couldn't really make any progress. So we have to selectively, choose the rules that we decide to follow today on a reasonable basis. So I really think that's a difference. But then in the end, it's also this, they have no needs. There are no real consequences for a computer. which of course makes it really challenging, again, from both this trust, but also from a kind of a safety perspective. So why do we trust that the pilots on the plane will actually take us safely back, or wherever we want to go? Well, we make the assumption that's a person sitting there that wants to survive as much as we do, and that they will do everything they can to save if there is a situation. Of course, this breaks down if the pilot does not care about their own life, so then we have issues. But now you replace that person with a computer. Why should we trust that? It doesn't care. So how should we trust that this will actually fly as safe as possible? Even though in practice, probably the computer is much better than people. And I've heard, I actually don't know if it's completely true, but basically is that if it's bad weather, basically the computer has to land. For example, if it's very low visibility and so on. And that most landings actually are autonomous. But there is a pilot in the plane, so that they have someone to save. But there's also, I mean, if it actually violates some laws, what should you do? There was a case in Switzerland, I think there was, they connected a computer to darknet and they started to buy guns and drugs and all these things. And the police came in and arrested the computer. And then a few weeks later, it's like, what should we do with this? And then gave it back. So it's like, how do you punish a system like this? There is nothing you can really do to it. So I really think there are some differences here. And now I'm out of time, but I'm not out of slides. So let's see. So I will try to very quick. So yeah, I think Europe has doing some things good. I mean, research is good. We have challenge on really scaling up AI in the private sector is one of the key things. So we have these ethical guidelines for trustworthy AI that we developed a number of years back. So I think that Europe has really taken an important and clear stance that yes, we do want AI, but we don't want any AI. We want AI that's human-centered, means that it should be beneficial to us as individuals and society, and we want to be able to trust it. And to be able to trust it, there are 3 properties that it needs to have. It needs to be lawful in the sense that it should follow the rules and regulations, which have some challenges, but and it should also satisfy 4 ethical principles. And what I do think is important and something that stands out is that good intentions are not enough. You also have to have a safe and robust implementation. And together, if you have all these 3, then you can claim that it's trustworthy. And the principles are quite straightforward. Respect for human autonomy means that we should be augmenting and complementing and empowering people rather than replacing them. Of course, we should prevent harm. They should be safe. They should be fair. However, if we can just agree upon what we mean by fair, equal and just distribution of benefits and cost, and it should be explicable. So we want to be able to have some form of understanding of how these systems work. And here there is a large variety of different approaches, from like transparency, understanding what is the data, who's behind this, to try to actually have some form of explanations of the output. And now in Europe, they're working on this AI Act, where they're basically proposing a legislation around AI. And it's a risk-based approach, which means that there are certain types of unacceptable risks. And here, one of the things that are being discussed is this remote biometric identification, which of course is very relevant to law enforcement, but also some other things. And then high risks are some, for example, medical and personal things where humans' lives and well-being are at stake. Then you have to have high requirements. And then the idea is that a large number of applications should be low risk or no risk, which means there should be much less regulation. And then the actual regulation is basically based on this ethical guidelines. And then I lead a research network where we are developing one of the 4 European AI Research Excellence Center networks, where we are developing the scientific foundations for trustworthy AI. So we are really working on this.
It's very optimistic to have all those slides in there.
It's like every time I give this talk, I talk for longer. I don't know why.
Yeah, I promised them to ask questions, you know, and I have zillions of questions
2,
here.
So I would just jump to the end.
And we're out in 40 seconds.
There you are.
Okay, there we are.
No, but I mean to kind of